Hey everybody, this is our movie for Heat Moves Conduction. We're really starting to focus on, we know that hot always goes to cold, and we're going to spend really the rest of this unit talking about how hot goes to cold and how that explains some of the things we see as people. At any rate, the very first question involves solid materials, and we need to spend a minute on that because we really haven't talked about solid, liquids, and gases yet. And I'm sure those are terms that you've heard many times before, and you've probably had them explained. The simplest definition of a solid is the state of matter where you're going to hold your shape. And think of a can of pop. The can part is a solid. It stays the same shape. The inside part, which is the liquid, the thing that you would drink out of a can of pop, if you pour it out, it'll spread. It'll either take the shape of the glass you pour it into, or it'll pour out on the floor or the like. So it's not obviously a solid. At any rate, I'm going to go to the Amplify lab for a minute, because it does a good job of showing at an atomic level or a molecule level what makes a solid a solid. And all of the stuff that we have in this sim are all solids. They're not liquids, they're not gases. And the key is, how do I know these are solids? How do I know they're not a liquid or a gas? And that's what we want to see. So I have cooled this sample off as cold as the simulation will allow me, which is 0 degrees Celsius, still way above absolute zero. Remember, if I could cool this off to absolute zero, none of these would be moving at all, because that's what absolute zero means. So while this is at 0 degrees Celsius, it doesn't mean it has no temperature. As long as there's movement, it's got some temperature. Okay, but what I want to do, I'm going to heat this up in a minute, but I want you to just focus out of all these little particles, molecules, atoms, whatever you want to call them that are in here. I want to focus on just one. Let's focus just on this guy right here that's in the corner. Okay, that's the one we're going to all look at right here. Let me erase that so we can see it real easy. Just watch that as I heat this up now. Just that one in the lower left corner. Now, if I add heat, you can see as it gets higher temperature, we know that these move faster, and that guy right there is bouncing around a lot more, but notice he is not changing his position, meaning he has not moved over to here. None of these are changing their positions. They are definitely speeding up. And if I want to speed them up more, I can take them all the way up to here, but this is still a solid. And again, I know it's a solid because none of these are changing positions. So let me slow it way back down again because it's easier to see when they're not going as fast. In a solid, all the particles stay in the same basic area. They still move, but they can't move freely around whatever they are. So in an aluminum can or a pop can or a solid like that, the atoms are moving because it's got a temperature, but they're not moving relative to one another. Now let's think about this idea with you guys as students. A good kind of analogy for a solid would be when you guys are in class at an assigned seat and you're following the rules and you're staying in those seats. Okay, you're still moving around a bit. You have to. Nobody sits in class like a statue. You wouldn't be able to do your work if you did. So you do have some movement, but if you're following the rules, you're not moving around relative to your other peers. You're always going to be in desk number this or that, and so will all of your peers. Now, when you move to the lunchroom, you're a little bit more like a liquid, which we'll talk more about later, but in the lunchroom, you can change your position. Now, during the first part of lunch, you still have to stay at the lunch tables, but you can move positions at those lunch tables, which you frequently do. That would be a better analogy for a liquid. So you have some freedom, but you still got to kind of stay in a little bit of the same spot. When we release you out to the field for honor time, that's when you kind of start becoming a little bit of a gas. You don't have total freedom. If you were really a gas, you could basically run down and go down to Finn Homes or anywhere in the harbor you wanted. We still make you stay on the field, but you can move around kind of wherever you want out there. That would be more like a gas. But again, in our simulation, the simulation always uses solid. There's never a point where this turns to either a liquid or a gas, and we know that because no matter how hot we make it, they can wiggle around a lot more, but they're still not changing positions. And in a solid, nothing can ever change position. That's what makes it a solid. That's what makes it hold its shape. Okay, so coming back here, use that information to answer question number 1. Then you're going to watch this movie on conduction, and then you'll go ahead and answer these questions, and we'll correct it when you're done. All right, thanks for watching.